Hey everybody, this is Larry. This is me going with Q3 of the weekly contest for 12 final array state after K multiplication operation 2. Yeah, hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. So this one, I actually solved. I mean, if you look at the, oh yeah, I forgot I put in the cheating thing. But I actually solved it about a minute or so after the contest. I want to say that it counts because there was like a 5 minute, or maybe not 5 minute, but I used like a 2-3 minute Leetcode delay, like was down or something. So that's my excuse. You can take it as you will. But I did solve this one maybe about 15 minutes or so if you count all the times up. But yeah, so this is the same as Q1, right? And if you already had the idea of using a heap, this will also help you using a heap, right? The key thing there are a couple of observations. First is that we need to mod. So, and you have to, when it says that you have to mod at the end, be sure that you mod only at the end. Well, you don't have to, but the logic has to be that you mod at the end and not during each step. Why? Because it changes the problem fundamentally if you are modding every step, because then the minimum value will be after the mod, right? So that makes the problem like ridiculous. But in any case, because that's why they allow you to mod after each of these, right? Okay, so that's one. Second is, of course, k is 10 to the 9, so you cannot do what you do in Q1, where that's k times n, too slow, right, obviously, or k times log n, still too slow. I would say for these kind of problems where you have to do a simulation, or they frame it as a simulation of really big k's, there are probably more ways to solve different components. But the first idea that I thought is about finding cycles, right? So finding cycles. The other idea that I might have is matrix exponentiation. I don't know if I'm spelling that right. Probably not, right? Yeah, okay. Matrix exponentiation, whatever, right? In this case, I didn't really see a way to get this part because you have to do min, and the way to kind of construct the matrix would have been to find cycles, and also n is too big to really, because matrix multiplication is going to be n to the fourth, oh sorry, n to the third. I saw 10 to the 4, and sorry, n cube, or obviously if you do your studying, matrix multiplication can be done in like 2.7 times, or n to the 2.7 or something like this, right? Like Strauss-and algorithm or whatever. There are a couple of faster ones, of course, but you're not going to even attempt them, right? And then you have to do it log k times. In this case, that's going to be just too much. So I immediately wrote that out, but that is something that comes up sometimes when you see a big k. So finding cycles. So there are many different ways of, this is a general idea. The idea here is it's not always the same idea, right? There are just multiple different ways. So, the thing is that you want to simulate something k times, but cycles will allow us to skip ahead some amount, and it doesn't always have to be just one cycle. Some problems may have different, but these are the ideas that we're playing with. And if you kind of think about for this I have to draw, so give me a second to bring up the drawing thingy. Where's my pencil? Oh, that's awkward. Oh no, there it is. So it's really simple. The idea is simple, right? I mean, it might be a little bit tricky, but the idea is simple, which is that you have some line, you have some really long line, right? Like let's say you're simulating from 0 to k. So this is k, this is 0. Then the idea here is that maybe if you can roll them up in some way, so then you could be like so this is 0, and then you have some cycles that allow you to cheap, and then it goes to k, right? So something like that, but it can So there are things that are like the what is called the row function or something like this, or the Freud's algorithm kind of thing, right? So you have this, and then something that looks like this, and then you're just trying to find out where k is on this. Sometimes it is the other way around, where it loops a few times and then it goes out, right? So you're at somewhere 0, and then something like this, and some combination. It could have multiple loops, right? Depending on this problem and so forth. So definitely these are things, yeah. But the idea about cycle finding, or whatever you want to call it, I actually don't know the actual name. I just call it cycle finding, but it's just kind of having a way to compress a lot of things, right? Because you know that you can't do it k times. You're just trying to find ways to do it. And then for this problem, the key idea is that you have a multiplier. All right, right. And what does this multiplier mean? This multiplier means that numbers will get big very quickly. That's 1. 2 is that after you run it a few times, let's say the simulation, we run it enough times, then what happens, right? So let's say you have a really small number, 1, and then you have a really big number, right? And then let's say the multiplier is 2, right? This is probably close to the worst case or something like, I mean, obviously with more numbers, but worst case idea, right? Then now you're just going to run this to 2, same thing, 4, 8, 16, oops. How many zeros did I have on this one? Oh, I did choose a billion. So yeah, so then now dot, and it's going to be 2 to the 30 is going to be greater than a billion, right? Okay, so what does that mean? And let's say we have a lot of numbers in between, right? I don't know, 5, 8, whatever, right? It doesn't really matter. And then the idea here is that all these numbers, it's going to be 1 times 2, right? 2 times, oh sorry, 5 times 2 to some other number, doesn't matter what it is. 8 times 2 to some other number, also doesn't matter what it is, right? Let's call it I, J, and K or whatever, right? So it's less confusing. So all these numbers don't matter, but what does matter is now that you've done them enough times so that they're all greater than a billion in this case, is that then now, let's say you have the biggest number, and then now the biggest number becomes the smallest number because you have so the idea is to simulate until all the numbers before the biggest number becomes bigger than it, right? What happens when it become bigger than it? Well, the multiplier still in this case is equal to 2. So let's say we put the number 1. What does that mean? Well, 1 is going to be 1 times some number. I mean, this is 2 to the 30, which we know. But let's just say 2 to the I. But what does this mean? This means that this number, after enough times, is going to be between 1 billion. Sorry, this is so hard to count. Okay, let's try again. Right, so this is 1 billion less than or equal to, I suppose. Is less than or equal to 2 billion, right? Because the idea is that 1 times 2 to the I minus 1 is going to be less than, I guess this case is going to be, I mean, for laziness, I'm going to write less than equal to. You could show why it doesn't actually matter that much anyway, because then just one of these should be only less than, whatever, right? So then now, the moment before, it is going to be this, and by definition, it is less than 2 billion, right? Which is the biggest number times 2. Why is that? Because, well, before that, it is smaller than a billion. So then if you kind of like, if you look at this relationship, right? And then look at this relationship, like it goes to from here to here, then it just means that you times 2 on both sides, right? So if you times 2 on both sides, this should be good. And then now, the thing is that this happens for every number, right? So that means that if you have 5 times for some number I minus 1 rather, then now when you times it by 2, this is still going to be less than the thing, right? The biggest number times 2, times the multiplier. Same for 8, right? Same for 10. So that means that, okay, so then now you have the smallest number. Smallest number is equal to, largest number when you start it anyway. And then becomes the smallest number at some point. So the largest number is equal to this. Largest number times multiplier is equal to, well, 2 billion, right? So that means that now, what does that mean? Well, let's rewrite all the numbers, right? In order. That means that when this number is the smallest number on the heap, what does that mean for all the other numbers? Well, if this is the smallest number, the largest number become the smallest number, that means that in this case, maybe you have 1 times 2 to the I, 5 times 2 to the, I don't know, J. This is not consistent, but you get the idea, hopefully, right? L. I'm running out of letters. But in any case, right, and then dot, dot, dot. So then now all the input, all the numbers behind it are going to be less than 2 billion, right? The largest number at the beginning times the multiplier, because of what we just said, right? So then now, what does that mean? That means that now when you do simulation, it will always do it in this order, right? Because then now, let's say you do one operation, then now it becomes here, right? Now it becomes 2 billion, and then now you do one more operation, then it's just this number moves up to here, right? Because it's going to be again next to here, and then it's going to be right? Like all the other numbers are by definition again going to be less than largest number times multiplier, right? So then now this goes this, and right, this goes here with the new I, new J, and new K, and dot, 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 right? So you get the idea. Then now so this is the cycle right here, right? Because then now so if we want to do this K times, we have what? K more times. What does this mean, right? This means that given that we have n, then we basically do this K divided by n times, right? So number of cycles is equal to K over n, because hopefully this makes sense, right? I mean, because this is just the number of total loops on all the numbers, right? And then maybe it's something that I call leftovers. Leftovers is equal to K mod n, which is basically just leftovers. And then for the leftovers, you do the first leftovers and then multiply them one more time, right? So just to kind of give you a visualization, if you have, say, K is equal to, I don't know, 20, and n is equal to, in this case, we have, say, 6, right? Let's just say 6, no dot dot dot, right? Then now that means that K divided by n is equal to 3 cycles, right? That means that we do the loop 3 times, because that's how, you do the math. And then we have 2 leftovers, right? And the 2 leftovers means that after doing them 3 times or 3 loops, we can do the 2 leftovers at the very end, right? We do it 2 more times. There are also, with the 2 leftovers, you can do them manually, but it also turns out that if you have a different visualization, you have this thing where you loop, or you simulate, you loop, and then you simulate again the leftovers. So you can do that too, kind of either explicitly or implicitly. So that's basically the idea for this problem. Yeah. There is some we'll go over the complexity and the proof in a little bit. But the first thing is that, and I got a TLE from this, just as time expired. So if I didn't get it, maybe I would have gotten it in real time. But it's that multiply is equal to 1, right? So everything that we said is true for every integer multiplier, except for if it's equal to 1. Because if it's equal to 1, then, well, the truth is that it doesn't even matter, right? Because if the multiplier is equal to 1, no numbers is changing. So just return nums. So that's a good base case. And oh yeah, and then there's mod at the end, but I think that's trivial. Yeah. So then now let's go over the code. So we start with getting the largest number. We do the heapify thing that we did in Q1. Right, we just basically push into the heap the value and the index, and then we heapify it, put it in a heap, and then we simulate until the largest number is the smallest number. So simulate until the largest number is about to be popped, right? So then now this is basically getting to the case where the largest number is now on top, and then you have all the other numbers lined up, and they're all going to be less than 2 or multiplier times the largest number. So the question that you may wonder is, well, wouldn't this possibly time out because k is still big? You think about the cycle loop thing that we visualized. Well, what if the beginning is just so big, right? So this is the part where you have to take a proof. The thing is that with the multiplier, if it's not equal to 1, this is why we have to can't put it in the thing. If it's not equal to 1, then it's going to be 2, right? Well, what does 2 mean? 2 means that the worst case with multiply by 1 is that the worst case is 1, and the other one is actually only 10 to the 9, right? So 1 in a billion. So again, we already kind of did this example. It just goes from 1 to 2 to 3 to 4, to 8 to 16 to 32 to 64 ... right? So all the way to 2 to the 30th. That means that at most, if this is going from 1 to 2 to the 30th, this takes 30 operations or things, right? For one number. So that means that in the worst case would have what's it, 10 to the 4th? I didn't even look. So you have like 1 1 1 1 1 ... 1 1 1 1 1 1, right? Because I think this is the part that is the scary part. And as a result, this is going to be log b, where b is the biggest number of bits, which is going to be 10 to the 9 or 30, right? So that means that at most this is going to be log b times, we have n numbers, and each log b iterations per number. We have n numbers, and each iteration takes log n times, right, from the heap, right? Because we have 2 heaps, this one, oops, the pop and the push, right? So 2 heaps. So that means that in total, this is going to be n log b time before simulation ends, right? Big O. But more critically, n is equal to 10 to the 4th, right? Log n is what? I don't know. 12 or something? No, like I'm so tired. Yeah, like 14, whatever, give or take, right? And then log b is going to be 1 billion, or b is a billion, so log b is 30, as we said. And that is, of course, if you multiply them all together, of course, as I plug into a calculator, is about 4 million. So, so that's going to be Gucci, right? And most cases are probably much faster anyway. So yeah, so that's basically why this is fast enough per se, right? And then next, now remember we always talk about invariant. So invariant here, the invariant here is that the first number, the top of the heap contains the largest initial number, or initial largest number, maybe, I don't know, right? And that's basically it. Yeah, and if you pop them in order, if you pop them in order, then this gives you the order in which you get the rest of them, which you can also use by simulation, but not a big deal. Yeah, and then cycles is what we said. Leftovers is also what we said. The leftovers in the cycle. I guess this could be n, because H should have n items. So this is kind of a little bit awkward actually. But yeah, and then for leftovers, we just multiply by the multiplier. For the rest of it, we multiply by the number of cycles, or the power of multiplier to the cycle. But remember the mod pow. Also remember to mod afterwards. Keeping in mind that if you're in other languages, you have to be way more careful than I do here. I know that at worst this is going to be less. This is going to be less than. Oh, sorry. This part is going to be less than mod. We also don't know that from here. This is at most 1 billion or 2 billion, I suppose. Right. But adding here, so 2 billion, 4 billion times mod, which is less than also another million, is it? Or a billion? I forget. Yeah, another billion. So that means that all this is going to fit in long if you're careful. But so I did think about it, but it doesn't get too big, at least in Python, which is good enough. So yeah. So what's the total complexity, right? So we said that this part is going to be O of n log b, as we said. This is just n log n, right? Where we pop everything, and then here it's just multiplying in both in O of n times, which is going to be good enough, so that we get dominated by this thing, which is O of n log b time, and O of n space, right? Which, you know, just using the heap, and I guess in a way, yeah. That's all I have for this one. I thought this one was pretty okay, honestly. I did it relatively quickly, but yeah. That's all I have for this one, though. I thought I did it pretty quickly. I think the key idea is just finding the loops, right? And as you can kind of realize, you can actually draw the loops in different ways. It's just about your visualization. But as long as you're kind of keeping track of everything in a good way so that you're not like off by one, you should be okay. And then the other part, of course, is just proving the bounds for some of these things to make sure that it is fast enough. Yeah. That's all I have with this one. Let me know what you think. Thanks for watching. And you could watch me solve it live during the virtual contest now. 210-0. Am I good? I hope so. Okay. Alright, how am I doing so far? We're probably not deep enough. Okay. So this is Q1, but with way bigger numbers. K is big. Okay, let's see. So this is otherwise the same problem. Should be maybe still be able to use this idea, because basically we're trying to find a cycle until every number gets multiplied again. Is that even true? Oh, only 442. I mean, that's the only problem with virtual, is that I almost wish they don't show us this, the total accepted part, because it's kind of a little bit of a spoiler on how hard it is. Also, this is 2 hard problems. Huh. I might skip ahead but let's see if I can think about this. Multiply can be big. I mean, what does the input number mean? We should be able to do like a thing, but with cycle finding, well, that's a hard sell. With n is equal to 10 to the 4th. And I'm going to skip ahead for a sec. Also 402, so I don't know. Alright, no time to no time to do this problem anyway. But at least we got cube 4, so we're not 100% too embarrassing. Just mildly embarrassing. Mod. I didn't even get to really think about this problem. But whew. I want to revisit that problem, but not now. I have 10 minutes. I'm going to upsolve this. I'm going to upsolve this, but it's still going to be quite a bit. 459 though. What's up here? Try to figure out the pattern. So this is my Q1. Right, I mean, so other than, obviously we need to think, but then that's going to be too slow. We just need to get the multiplier such that it gets okay, let's say you run this n times. No, I mean, maybe even like, so you want to get the smallest number such that it gets the bigger the number. Then now every number is between multiple, and then now you can do it cycle times, right? Okay. I mean, I don't know if I have enough time for it, but we'll do best efforts, right? Yeah. Maybe just greater than 0. Okay. And then now we want to say smallest, whoops. So I want to get the index though. And it could have multiple same numbers, but yep, this is wrong, Larry. Okay, so then now we do this. If x is equal to smallest, actually we only need a count. I mean, if I have enough time, this is actually not that bad, I think. But Is it true though? Can you, if it's 2, then now it's going to be whatever, but then let's say you have 3 and 4, or 2 and 3. You have 4 and 6, 6 and 8, 12 and 16, 24 and 32, and then eventually 42. No, we'll never catch up, right? Or you never need more. Okay, yeah, no, this is the right idea, but I ran out of time on it, probably. 4 minutes left, but we'll upsolve it though. Yeah, I mean, every heap pop is going to be the smallest. So then now we just have to count the smallest one, right? So then now, yeah, that's okay. But we want to make sure that, okay, so I guess the first time we want to get the largest, actually. Then that means that all the numbers smaller than largest is good. Right. So then now we have k left, and we just want to distribute it, right? Okay, so then ordering is going to be, you go to just order of heaps. Something like this. Okay, so then now we have k left. So then now we have just gonna be out of time, which is a little bit sad, but that's not a big deal. So then cycles is just equal to, so k left divided by length of ordering, and then leftovers is just equal to k mod length of ordering. Okay, and then now order, okay, for I in range of leftovers, we want to say ordering sub I, we multiply by multiplier, right? Oh, not ordering sub I. Ordering sub I is going to be the index, so then it's nums of order. Okay, and then all the other ones by cycles. So it's going to be pow of multiplier, cycles, and then mod, right? And then nums of I mod. Oof, and it's not defined. And that's not right. I was going to do YOLO submit. There's a minute left. Maybe I could still YOLO submit. K is equal to 2. So, okay. I mean, I guess I ran out of time because I spent a little bit too long on Q3, or Q4 rather. Okay, so 3 cycles is pretty wrong. Because K is, oh no, K is 10,000. Okay, no, wait. K is 2, so this is just weird. Oh, why do I have increment here? Wow. Okay, that is just a silly typo. Still wrong, but I think we're off by... maybe off by a little bit. So we have K is equal to 1, ordering is... Ordering is off. It should be 1 and 0, so that's why this is off. But... oh, because this is break. We have a print statement. YOLO submit. I think I just missed it, but it may be wrong anyway. But you know, I wanted to give it a YOLO attempt. Maybe it's times out. Why does it time out? Oh, because multiply is equal to 1. Right. If that's the only case, then I am very sad. But oh. Alright. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, this video, everything in between. Stay good, stay healthy to your mental health. I'll see y'all later and take care. Bye bye.